Jack it up.
Okay, ready to dive into some serious math.
Let's do it.
Today we're tackling one of the most famous problems in like all of math history, right?
Absolutely. It's a problem that haunted mathematicians for, well, literally centuries.
Sounds intense.
It is, but also super fascinating.
All right, so no more suspense. Let's just lay it out there. What exactly is Fermat's last theorem?
Okay, so imagine this equation. A to the n plus b to the n equals c to the n.
All right, I'm following so far. It kind of looks like the Pythagorean theorem, right?
Oh.
A squared plus b squared equals c squared.
You got it. That's the relationship between the sides of a right triangle.
Right. I remember that from, high school geometry and all.
Exactly. So Fermat's last theorem is like the rebellious cousin of the Pythagorean theorem.
Rebellious, huh? Okay, I'm intrigued.
So with the Pythagorean theorem, a squared plus b squared equals c squared, there are tons of whole number solutions.
Like 3, 4, and 5, right?
Yeah, exactly. Those are called Pythagorean triples.
I vaguely remember that term.
But here's where things get wild. Fermat comes along and says, nope, bump those exponents up above 2, even just a little bit.
Like a cubed plus b cubed equals c cubed.
And suddenly, he says, there are no whole number solutions.
Seriously? Just like that?
Yeah, he basically dropped this mathematical bombshell. And to make it even more frustrating, he claimed he had a proof but never actually wrote it down.
No way. He was like, I've got the answer, but you'll have to figure it out yourselves.
Pretty much. He left this little note in the margin of a book, and that was it.
Talk about a cliffhanger.
You can say that again. And that little note launched a mathematical quest that lasted for centuries.
Okay, I gotta know more. Where do we even begin to unpack this? It seems so simple, but then so impossibly hard at the same time. Like, what's the big deal about finding whole number solutions anyway?
It's a great question, and it gets at the heart of what makes Fermat's last theorem so profound. On the surface, it seems like a puzzle about finding the right numbers. But underneath, it's about something much deeper. It's about understanding the very nature of numbers themselves, the hidden structures and patterns that govern how they behave.
Okay, I'm starting to get it. It's not just about arithmetic. It's about unlocking some fundamental truth about the mathematical universe.
Exactly. And the fact that such a simple-looking problem could lead to such deep mathematical insights is what captivated mathematicians for so long.
It's like Fermat opened a door to a whole new world of mathematical exploration.
I like that. It's like he pointed to a distant mountain peak and said, the view from up there is incredible, now go find a way to climb it.
And did anyone manage to reach the summit?
The journey to the top was long and winding, full of brilliant ideas, dead ends, and unexpected breakthroughs. It took centuries of mathematical innovation to finally reach the peak and conquer Fermat's challenge.
Okay, now I really got to hear the rest of this story.
We'll get there. But before we delve into the solutions, let's take a step back and explore some of the early attempts to crack this mathematical enigma.
All right, let's rewind the clock a bit and see how mathematicians first grappled with this seemingly impossible problem.
Because even those early attempts, though ultimately unsuccessful, led to some pretty remarkable mathematical discoveries. They started to uncover the hidden depths of Fermat's challenge, revealing the need for entirely new approaches and ways of thinking.
I'm all ears. Take us back to the beginning.
Well, in the years after Fermat scribbled his famous note, you can imagine mathematicians were pretty obsessed. They were probably thinking, there's got to be a simple solution, a counterexample that proves Fermat wrong.
Right, like, come on, Fermat, you must miss something.
Exactly. But as they started digging deeper, they realized this wasn't some easy riddle to be solved with basic arithmetic.
So just plugging in bigger and bigger numbers wasn't going to cut it.
Not a chance. It became clear that proving Fermat's last theorem required a more theoretical approach, a deeper understanding of the underlying structure of numbers.
It's like they needed a whole new set of tools to even approach the problem.
Exactly. And that's what makes the history of Fermat's last theorem so fascinating. It's a story of mathematicians pushing the boundaries of their field, inventing new concepts and techniques in their pursuit of a solution.
So what were some of those early attempts? Did anyone make any headway?
Well, even though a complete proof remained elusive for centuries, there were some significant milestones along the way. For example, in the 18th century, mathematicians like Euler and Legendre managed to prove the theorem for specific values of n.
Like a when equals 3 or 5.
Precisely. And these weren't just minor tweaks to existing ideas, they developed some really intricate arguments, using techniques that hadn't been explored before.
So they were chipping away at the problem bit by bit.
In a way, yes, but what's interesting is that each of these proofs was unique to the specific exponent it tackled. There wasn't a single method that worked for all values of n.
So as mathematicians proved the theorem for higher values of n, like 7 or 11 or whatever, did the proofs just get more and more complicated?
Exactly. It was like climbing a mountain, where each step gets steeper and more treacherous.
And remember, we're still talking about the 18th century here, right? We're still centuries away from a complete solution.
That's right. The story of Fermat's last theorem is a marathon, not a sprint.
And I have a feeling we're just getting started.
You're absolutely right. There are still many twists and turns ahead, some brilliant minds to meet, and some incredible mathematical breakthroughs to explore.
Okay, so these early mathematicians were making some progress, but it sounds like they were hitting a wall. Like, were they just stuck using the same tools over and over again, just, getting more and more complex?
That's a great observation. And it gets at a key turning point in the story of Fermat's last theorem. You see, to really break through, mathematicians needed to develop entirely new tools, new ways of thinking about numbers.
So what kind of tools are we talking about? Did someone invent a new kind of calculator or something?
Not quite a calculator, more like a new way of looking at the very fabric of numbers themselves.
Okay, that sounds pretty abstract.
It was. One of the key players in this revolution was a 19th century mathematician named Ernst Kummer.
Kummer, all right, I've heard that name somewhere before, but remind me.
Kummer was wrestling with some really fundamental concepts in number theory, specifically this idea of unique factorization.
Unique factorization, okay. I'm pretty sure that was not covered in my high school math class.
Fair enough. In simple terms, unique factorization means that any number can be broken down into a unique product of prime numbers. It's like each number has its own special fingerprint made up of primes.
Okay, I think I kind of get that. 12 is 2 times 2 times 3, and that's the only way to break it down using prime numbers.
Exactly. But Kummer realized that this whole unique factorization thing was breaking down in certain number systems he was working with.
Wait, hold up. You're saying unique factorization doesn't always work? Math can just, break down sometimes?
Well, not break down exactly. It's more like the rules change when you start playing in different mathematical playgrounds.
Okay, what kind of playgrounds are we talking about?
Kummer was working with something called complex numbers.
Oh, right, complex numbers. Those are the ones with the imaginary unit I, where I squared equals -1.
You got it. And in the world of complex numbers, things can get a little, complex. The usual rules of arithmetic don't always apply in the same way.
So unique factorization was hitting a snag in the land of complex numbers.
Exactly. And this led Kummer to develop some really groundbreaking concepts. He invented something called ideal complex numbers to try and fix this factorization problem.
Ideal complex numbers. It sounds like he was trying to create, the perfect complex number system.
Sort of. He was trying to create a system where unique factorization would still hold true, even in this more complex world. And his work led him to distinguish between different types of prime numbers, regular and irregular.
Regular and irregular primes. Is that, the good ones and the bad ones?
Not good or bad, just different. Regular primes played nicely with unique factorization, even in the complex world. But irregular primes caused trouble.
So Kummer's work was all about sorting out the primes, figuring out which ones were well-behaved and which ones were causing a ruckus.
You could say that. And here's the key connection to Fermat's last theorem. Kummer was able to prove that the theorem holds true for all regular primes.
Whoa, hold on. He proved Fermat's last theorem, but only for regular primes.
That's right. It was a huge breakthrough, a major step forward. But those darn irregular primes were still a major obstacle.
So it's like he conquered half the mountain, but the other half was still shrouded in mist.
A great way to put it. And unfortunately, proving the theorem for irregular primes turned out to be way more difficult. It was like mathematicians needed a whole new map, a new set of tools to navigate this uncharted mathematical territory.
So did that map eventually appear? Did someone finally figure out how to deal with those irregular primes?
They did, but from a completely unexpected direction. The solution, or at least a crucial part of it, came from a connection to a seemingly unrelated area of mathematics.
Okay, now you've really got my attention. What could Fermat's last theorem possibly have to do with, other parts of math?
That's what makes the story so incredible. It involves this really wild idea called the Taniyama-Shimura Wile Conjecture.
Okay, that's a mouthful. I need some help unpacking that one.
Fair enough. It's a bit of a brain twister, but basically this conjecture proposed a deep connection between two seemingly disparate mathematical objects, elliptic curves and modular forms.
Elliptic curves and modular forms.
Elliptic curves and modular forms. I'm pretty sure I've never even heard those terms before.
No worries. We're going to break it down. Imagine, just for a moment, that you have a donut.
Donuts. Okay, this deep dive just got a whole lot tastier.
So you've got this donut, right? And you slice it in a particular way that creates a closed loop, like a circle on the surface of the donut.
Okay, I'm picturing it.
That loop, that shape, can be described by a mathematical equation. That equation is called an elliptic curve equation.
So it's like the math behind a donut slice. Exactly. And these equations are really interesting because they have some unique symmetrical properties. Like you can rotate or reflect them in certain ways and they stay the same.
Okay, so elliptic curves are like the math of symmetrical donut slices. Got it. What about those modular forms? They sound even more abstract.
They are pretty abstract. It's hard to picture them in a concrete way, but you can think of them as functions that have incredibly high levels of symmetry. Imagine a snowflake, how it has a beautiful repeating pattern that stays the same even when you rotate or reflect it. Modular forms are kind of like that, but their symmetries exist in a much more abstract mathematical space.
Yeah.
Like they're snowflakes living in a world with like a million dimensions.
Okay, my brain is definitely doing some mental gymnastics here, but I'm trying to keep up. So we've got these symmetrical donut slices and these super symmetrical multidimensional snowflakes.
Right.
What on earth do they have to do with each other?
That's the brilliant part. The Taniyama-Shimura Wile conjecture proposed that every elliptic curve could, in a sense, be transformed into a modular form.
Wait, you're saying those two things are actually connected? Like they're two sides in the same coin?
Exactly. It's like saying that these two seemingly different mathematical worlds, the world of elliptic curves and the world of modular forms, were actually secretly intertwined.
Okay, I gotta say, this is getting pretty mind-blowing. But I still don't see how it connects back to Fermat's last theorem. Like, how do those weird symmetrical shapes help us with finding whole number solutions to that equation?
That's where things get really, really interesting. And that's what we'll dive into right after a quick break.
You're watching Sassy Scoop TV. If you're enjoying this podcast, don't forget to check out more of our videos for exciting content. And if you like this one, hit the like button, subscribe to our channel, and drop a comment below. We would love to hear from you.
So we left off with this crazy connection between elliptic curves and modular forms. But like, how does any of that help us with Fermat's last theorem? I'm still kind of lost.
Well, this is where it all comes together, and it's seriously mind-blowing. In the 1980s, a mathematician named Gerhard Frey came up with this wild idea. He basically said, imagine for a second that Fermat was wrong.
Okay, let's pretend Fermat messed up. Then what?
Frey said, if there was a solution to Fermat's equation, a solution that broke the rules Fermat laid down.
Like, if you could find some magic numbers that actually worked for a greater than 2?
Exactly. Frey realized you could use those magic numbers to build a very specific kind of elliptic curve. And this curve would be so bizarre, so unlike any other elliptic curve, that it would basically break the Taniyama-Shimura Wile conjecture.
Whoa, hold on. So Frey was saying, if Fermat's wrong, then this weird curve exists. And if this weird curve exists, then Taniyama-Shimura Wile is wrong too.
You got it. He basically linked the fate of Fermat's last theorem to the fate of this whole other conjecture.
It's like a mathematical domino effect. Knock down Fermat, and Taniyama-Shimura Wile falls too.
Exactly. And a few years later, another mathematician, Ken Ribbit, rigorously proved that Frey's intuition was right. He showed that if you could find this weird Fermat-breaking curve, it would absolutely shatter the Taniyama-Shimura Wile conjecture.
Okay, so now the stakes are even higher. It's not just about Fermat anymore. It's about this whole web of interconnected mathematical ideas.
And that's when Andrew Wiles, a mathematician who'd been fascinated by Fermat since he was a kid, steps onto the scene. He'd basically been working on the Taniyama-Shimura Wile conjecture in secret for years, and he realized that if he could prove this conjecture, well,
he'd automatically prove Fermat's last theorem, too.
Bingo. It was like finding a secret passageway that led straight to the summit of Fermat's mountain.
So Wiles dedicated himself to proving Taniyama-Shimura Wile. What a challenge.
It was a monumental effort. Years of work, tons of complex math, false starts, and dead ends. But finally, in 1993, he announced he had a proof. The mathematical community was absolutely buzzing. Could this 350-year-old problem finally be solved?
I can only imagine. But wait, didn't something go wrong? Wasn't there an error in the proof?
Yeah, there was a twist in the story. During the peer review process, a gap was found in Wile's proof.
Oh no, was it a fatal flaw, like back to square one?
It wasn't a complete deal breaker, but it was a serious problem that needed to be fixed.
So what happened? Did Wiles just throw in the towel?
Not a chance. He's a true mathematical hero. He went back to work, teamed up with another mathematician, Richard Taylor, and after another year of intense effort,
They patched the hole.
Yep. In 1995, the corrected proof was published, and Fermat's last theorem was finally laid to rest.
What a journey. So after centuries, Fermat's challenge was finally conquered. End of story, right?
Well, not quite. Remember, Wiles focused on proving a special case of the Taniyama-Shimura Conjecture. His work laid the foundation for proving the entire conjecture, which is now known as the Modularity Theorem.
Right. The Modularity Theorem. That was a big deal, wasn't it? But, refresh my memory. What exactly is the Modularity Theorem?
Well, in simple terms, it states that all rational elliptic curves are modular.
Okay, I'm going to need a little more than simple terms.
It's basically saying that all these elliptic curves, these mathematical donut slices we were talking about, can be paired up with a corresponding modular form, one of those supersymmetrical, multidimensional snowflakes.
Okay, so it confirms that deep connection we were talking about.
Exactly. And it turns out that this connection is much more profound than anyone initially realized.
So it wasn't just about solving Fermat's last theorem. It opened up a whole new world of mathematical exploration.
Exactly. And the ripple effects of the modularity theorem are still being felt today. It's had a huge impact on lots of different areas of math and even physics, like string theory.
Wow, so Fermat's scribbled note in a margin led to all that.
It's incredible, isn't it? Sometimes the most abstract-seeming problems can lead to the most profound and unexpected discoveries.
Absolutely.
Yeah.
But there's still one thing I'm wondering about. Do you think Fermat actually had a proof? Like, could he have really solved this problem back in the 17th century?
That's the big question, isn't it? The proof we have now, the one Wiles and others built, is super complex. It relies on tons of mathematical concepts that just weren't around in Fermat's time.
So it's kind of hard to imagine him having a proof back then.
Most mathematicians think it's pretty unlikely. Maybe he had a flash of insight, a partial idea that he thought was a complete proof, but it just didn't hold up.
Or maybe he stumbled onto a totally different, elegant solution that we just haven't discovered yet.
It's a mystery that might never be solved. And that's part of what makes Fermat's last theorem so enduringly fascinating. Even though it's been proven, it still sparks our curiosity and imagination.
Well, I gotta say, this whole deep dive has been a wild ride. I never thought I'd get so excited about, number theory and elliptic curves and all this crazy math stuff.
Math can be pretty amazing when you dig beneath the surface. And who knows what other mathematical mysteries are out there just waiting to be discovered.
I'm ready for the next adventure. But before we go, a huge thanks to you for taking us on this incredible journey through the world of Fermat's last theorem.
My pleasure. It's been fun exploring this mathematical marvel with you.
And to all our listeners out there, don't forget to like, subscribe, and leave a comment below. Tell us what you thought of this deep dive and what other mathematical mysteries you'd like us to explore. Until next time, keep those brains buzzing.